And we're live. Hey everyone, this is Xibei from DoraHacks. Thank you all for joining us today for the second demo day of the DoraHacks Space Resources and Exploration Grant. Today we have Yue representing the team from Imperial College London, who's building the ETW system for ISRU Beneficiation. He's one of the winners of our Space Resources and Exploration Grant Round 1. And today we're very excited for his demo. But before we kickstart the demo, let me just give you a quick introduction about who we are and just an overview of the grant's background. So for those who don't know DoraHacks quite well enough yet, we are a global hackathon organizer and one of the world's most active developer incentive platforms. We'd love to support innovation in blockchain, quantum computing, space tech, and many more. And we provide a wide range of toolkits to help developers around the world team up and fund their ideas and projects via hackathons, grants, bounties, etc. And this Space Resources and Exploration Grant is actually a long-term initiative by DoraHacks to foster innovation in space tech. We just successfully concluded our first round, supporting 2 amazing projects. It's a significant milestone for us, as is the very first time DoraHacks has ventured into supporting space tech innovation. So yeah, we're super excited to have Yue here with us today. As we are very much committed to supporting innovators in this exciting frontier, this grant program is definitely going to be a long-term focus for DoraHacks. So right now, the second round is actually already open for submissions, and it will stay open until August 11th. The prize pool for the second round is up to $10,000. Every promising project stands a chance to win a minimum of $1,000. So we love to call all the space engineers and enthusiasts who are building within the space tech sector to join us. It's a very unique opportunity for those who are passionate about space resources and exploration. And we can't wait to review all the submitted projects. So now let's give a warm welcome to Yue, who will present his winning project, the ETW system for the beneficiation process of ISRU. The project's ultimate goal is to build a sustainable system for transporting and separating lunar particles on the moon in large quantities. And for the audience who's with me here today, during the demo session, please feel free to share any questions you have in the YouTube and Binance Live chat room. I'll make sure to ask you your questions. So now, without further ado, I'm excited to hand over to Yue to present his demo. Please take it away, Yue. Welcome.
Okay, thank you. Thank you for the introduction, Xibei, and thanks for the support of DoraHacks. I feel grateful to share my work with you, with our community. Okay, can you see my screen?
Yes, we can see it perfectly.
Cool, thank you. Okay, so thank you very much again. Today I'm going to do a brief introduction for my project, which is to build a ETW system for the beneficiation process of ISRU. The presentation is divided into 5 sections. I will first introduce the background and beneficiation process of ISRU, and then it's our method. Following our method, I will introduce the latest, our simulation results and experiment results. Finally, is the conclusions of our presentation. In situ space resource is the use of natural resources from the Moon, Mars, or other bodies for use in situ or elsewhere in the solar system. We don't rather than bringing all the resources from the moon to the Earth. It's too cost. So the best way is to use the resource on the moon, do the excavation, mining, and production of all the needs that we want. The federal target of ISRU is for people to live in space, and also we can use this human space in the space for further travel. In addition, this is also a potential for space business like the payload and also the rocket, the design of this. For the in-situ space resource utilization, we need to know what we need now. Generally, there are all kinds of different kinds of resource on the moon, like metal, volatile, and other minerals, like the oxygen and carbon. The usage is basically divided into 4 sections. First is for human consumables, and also we could use this metal due to manufacturing and construction. Finally, is the propellant, like for another launch for the rocket. We can't bring all propellant from the Earth. If we run out of the propellant, we want to make use of the resource on Moon or on Mars to reproduce propellant for our rockets for another launch. And the current, the most important material or the resource we want to extract is water, because water is the first need for human consumables, and water also can be used to produce hydrogen and oxygen. This could be used for the propellant. After we get the basic consumables and propellant for rockets, we could consider the further technology. The first part is the 3D printing. It's one of the technology that could make the manufacturing or construction for the machines. We could generate this machine by using the 3D printing technology. Within this machine, we could do the production of other materials that we want. The final target, of course, is the space-based, the manufacturing, industrial construction to have further flexibility to get more energy or resources. Since in-situ space resource is quite broad and it needs a combination of many different complex technology, our focus is on the beneficiation process of ISRU. Let's first have a look at what we have on the moon. This is a sample brought by Apollo project. This indicates the shapes and the compositions of the materials on the moon. For example, we have these different kinds of materials. However, sometimes we only need one of them to get what we want. Currently, for this material, ammonium is the most desirable mineral that people want to take use of. Ammonium is in this fraction. However, if we just collect all the materials on the moon and put all the materials into the production machine to generate like the iron, water, it's not so efficient. But if we can extract ammonium from all the materials, do the beneficiation process first, then we could get high efficiency production. So ISRU it's like analogs to that of the terrestrial mineral extraction. The beneficiation process of ISRU also is a mineral process. This is used extensively at huge scale in the terrestrial mining industry to separate minerals of different types. But for any ISRU on the Moon or Mars or asteroids, it's the same process. So the beneficiation process is a key stage of the entire process of ISRU. Our project is mainly to focus this process to do the mineral processing, which could increase the production efficiency. This is a flow sheet designed by my supervisor, and it's also applied for the universal flow sheet of ISRU process. Within this beneficiation process, we want to generate this special conveyor that could be used for the transport of the minerals that we extract from the moon. And also this special conveyor can also do the beneficiation process, which is also the particle separation process, like to separate different size of particle into different output, like big particles going to the first output, the other small particles going to another output. This is quite like magic special conveyor, right? But actually, we could make this type of conveyor. The method we use is called electrostat traveling wheel method. In this video, we can see there is a screen board, which is the key part of our system. It's as the conveyor of the system. We put these white powders on the conveyor, and these three cables can input the high voltage to the electrode, which is the conveyor. By applying the high voltage, we could generate a high intensity of the electric field. And without any initial process, we just activate the system, we could transport these particles. Because of the technical issue we can't play on this PowerPoint, I will switch the window to the video window. We can play again. So we can see these powders move very fast, and by the observation of our eyes, there's no particle left on the board. So the transport is very effective. The right finger illustrated the basic mechanism of the system and how we construct the system. So the right electrodes are shown as the yellow bar. This yellow bar illustrates the parallel electrodes, which can be divided into 4 groups. These 4 groups of electrodes are connected to the different phase of the output of voltage. Here we use a function generator that can control the output of high voltage, like the amplitude, frequency, and waveforms. In this way, we can control the electric field here. By the control of the electric field, we can design the parameters of the electric field, and then we can control the trajectories of particles and make them move as we want. In order to better understand the particle motion, how our operating parameters and system parameters affect particles motion, we used a high-speed camera to record particles motion in this pink square area. Below shows the superimposed frames, like we superposed different frames in a single photo, so we can observe particle trajectories in details. By doing our experiment, we have classified particles motion into 3 main motion modes. So all the different kinds of particle motion can be divided into these 3 typical motion modes. Like in yellow one, the particle levitates in the air without contacting with the conveyor. This kind of particle is quite small, and the electric force can make particle overcome the effects of gravitational force and make particle keep flying in the air. For particle with larger size, it will drop because when particle fly away from the electric field, fly over the surface, the intensity of electric field will decrease. So at the decrease of Coulomb force, the gravitational force will drag particle into the surface. And this illustrates the alternating falling and bouncing motion. For particle with even larger size, It's so large, so the gravitational force drags particle stick to the surface, and the Coulomb force, the electric force, can only make particle move left or right. This is called surfing mode, like people surfing in the sea. Our experiment has classified the particle's motion modes into 3 typical motion modes, which could help us to analyze particle's motion in this field. In addition to the experimental results, we have done the simulation model. This simulation model is a 2D physical model, physics-induced model, which can be used to estimate and predict particles' trajectories in our system. We don't need to do all the tests for different designs of the parameters, which is so cost. Within our system, we can choose whatever the parameters that we want, and then we just input our parameters into the system so we can get the performance of the particles using our system. The right figure illustrates an example showing that the relationship between particles' velocity with frequency at particle size. The different colors in this red bar indicate the particles' different movement velocities. We can see within this figure, we can see how our frequency, how the operating parameters affect particle's motion velocity, and how it's related to the particle size. Like for the bigger particle, for the particle with high frequencies, particle's motion velocity is quite small, like in the green, it's quite small. With lower frequency, particles get higher velocities in this red area. However, in some area, in this deep blue area, this deep blue area indicates that particle has negative velocity. This negative velocity means that particle moves in different directions. This could be a very good phenomenon for us to separate particles. Like if particle at this frequency, the bigger size one move in this direction. For the small size, like less than 18 micrometer, particle move in another direction. So the small size of particle and big size of particle moves in different directions. This could be used to separate particle with different sizes. Here we also use the sample polyethylene to record particle's motion. We also use the high-speed camera to record motion of particles. This is also a superimposed frames for a single particle. Like we use 10 frames in a single photo. By calculating the trajectories and time that particle used, we could calculate particle's velocity. We can say particle velocity is quite high. And here we use the frequency at 30 Hz and 60 Hz. The calculated trajectories is quite close to the wave velocity at 30 Hz and 60 Hz, which confirms that the particle can move quite efficiently with the electrostatic traveling waves. Sorry, I didn't explain much about traveling waves, but traveling waves means that the waves has a direction, and if particle has high charge in this wave, it could travel with the same direction of the traveling wave. So this simulation result, this experimental result confirms that particle can travel along with the same direction of the traveling wave. Here is another example showing the high load. We put a high load on the surface, and we want to confirm the high load transport ability of our system. Generally, if people put large mass on the surface, the higher particle will have pressure on the lower particles. So it's very hard for particle to be transported. And also, this system is a non-mechanical system. So if we could transport this high load mass of particle within our system, it could be quite great. And here we used a particle size between 70 to 110 micrometer. These particles are all in this range. And what voltage that we use is 1000 volt and 1500 volts. We put about the 5 or 10 gram on the surface, and we can see here is another video. We can show the high efficiency of the transport ability. From this video, we can see this particle can be transported quite fast, and the lower and upper particle can be both be transported. So this experiment has confirmed the high node mass transport ability in our system. But our final target is it's not only to transport particles, but also separate particles. So in the second experiment, we have shown the particle separation results. We have made a mixture of 0.5 gram of small particles and 0.5 gram of big particles. We mixed the small size particle and big size particle together, and we use this finder to feed particle into our surface. And then by activate the system, we put 2 boxes at the right and left side to collect particles. And the forward means the same traveling wave directions, means the direction with the same direction of the traveling wave. In the forward direction, we could collect 0.4 gram of small particles and very few of big particles. In the backward direction, we could collect 0.21 gram of big particles and very few of small particles. This result shows the high separation efficiency of our system. Based on these parameters, based on these results, we could also calculate the concentration of the particles. So in the forward direction, we have the 87% of the concentration of small particles, which is calculated by this 0.4 gram divided by the combination of 0.4 and 0.06. In the backward direction, we could get very high percent of the concentration of the big particles. And for the recovery, like if we put 0.5 gram small particles, we could get 80% back of the small particles. But for the big particles, the recovery rate is quite low. It's less than 50%, because for big particles, there's frictional force and air drag force, which may hinder the particle's motion. Some big particles may still stay on the surface. However, if we do our experiment in the vacuum, like on the moon, the frictional force and air drag force, there's no air drag force because there's a vacuum on the moon. So this could largely increase the recovery of big particles. We have also considered other ways to increase the recovery rate of the big particles, like we could add some vibration underneath the board. Also, we could tilt the conveyor, make there's an angle, so big particles so there's a gravitational component along the surface, which could make particles travel down from the surface. And for the small particles, because the Coulomb force is quite high, so this can make small particles overcome the gravitational force and fly higher to the box. There are several ways that we could use to increase the recovery rate. Finally is the concurrence. This electrostatic traveling wave method is quite useful and has a wide range of applications. I haven't introduced this before in the previous slide. Here I can do a brief introduction here. By using the electric field, there are some applications to the biological cell separation. The cell has polarity, so if we could generate an electric field in the fluid of the cell, the cell can be separated by the electric field. Also, the solar panels. With the long-term use of the solar panels, there will be dust accumulated on the surface, which will decrease the efficiency of the production of solar energy. Generally, people will use water to clean the surface. It's quite water consumable, and in somewhere like in desert or in the space, on the moon or on Mars, there's no water. Water is very valuable. However, using our system, we could put a parallel of electrodes underneath the board. So if the dust particle come close to the board, our system can repel these dust particles automatically. It's quite good. It's quite economic. And also, it's the beneficiation process. We could use our system as a potential beneficiation process for the resource on the moon, do the mineral processing, particle separation, this kind of process, which could be used for the further ISRU process. And in our research, we have done theoretical development. First, we built a physical model. It's 2D. We can estimate and predict particles' motion mode. By using the results, we could design our systems. Also, we have done experimental research. We use high-speed camera to record particles' motion in details. Also, we did theoretical analysis like the DP analysis, which is DP is related to particle size and field frequency. This could help us to separate particles with different sizes. Finally, we have experimental demonstrate that we could transport high-load, large mass of particles, and also we could do the particle separation by size. Finally, is the key conclusions from our project. Experiments have been done to explore the particle motion modes, and a detailed simulation model is provided to analyze and predict particles motion in this field. The ability for the transport of particle has been verified, and different sizes of particles have been separated in terms of different motion directions. And this, we have also attended many different conferences in the space area, like we have presented in the Space Resource Week this year in Luxembourg, and we have attended the 23rd of Space Resource Roundtable in Colorado School of Mines. This is our team. These are my supervisors. The 3 people are my supervisors. Young Senior is the professor at Imperial, and he's also a fellow of the Royal Academy of Engineering. My second supervisor is Catherine. She now is the director of the ISRU. Stan works as a consultant in our group. He retired from the NASA Kennedy Space Center. This is me. I'm currently in my third year of my PhD at Imperial. So that's all. Thank you very much for your attention. Welcome any questions and comments, and welcome to contact with me. Here's my email address. Thank you very much again. Okay, seems there's another technical issue, and we could wait for a while. Okay. Hi everyone. I I just received message from the host. She has several questions. Like the first one is that if I what kind of challenges we have met and how we overcome these challenges. First, I want to introduce the background of this method. This method is quite new. Like the very original concept is on a LASA report in 1967. They want to do the dust mitigation, dust removed from the solar panels. This is original idea where it came from. So they put forward this kind of method. Like we put a parallel of electrodes underneath the board, so this could repel the particles automatically. It's in 1967, but at that time it's only a concept. They haven't done any experiment design or simulation. It was only a concept, and until 1987, people called Mazumder. So it's in an American university. In their group they have designed experiment system, but their experiment system is not for the dust mitigation of solar panels, but on the biological cell separation, like I introduced in the fellow slide. They use their system, and they build their system in a fluid, because the cell is easier to be transported in fluid. So their system is designed to transport the biological cells and want to do separation. And in the 21st century, a research group in Waseda University in Japan, a professor called Kamodo. They have done a lot of experiments and designed the system to transport particles, like I did here. Their research area is quite broad. Their range is quite large, so they have done so many different designs of a system. They not only do this parallel design, they like do a circle of electrodes. They have tried different ways to transport particles, and control their trajectories. So this method, according by their research, this method has gained increasing attention. And then in the late recent years, a research group in France and in America, in Boston University, they have done similar research to do the experiment, trying to transport particles with larger mass because I will say how we return to the challenges. One of the challenges is the large mass, high load. Like initially, they could only remove very few particles. If there is high load, the top particle will have pressure on lower particles. So this is the first challenge. Initially, only very few particles can be transported, but this is the first challenge. And in our research, we also in the initial stages, we could only transport small particles. But we want to overcome the challenge. We want to increase our transport ability. Then my supervisors and I have done the literature review. We have published a paper about this method. We have read all the papers published, and we have found the gaps. The first gap is that people want to do the experiment first, but the basic mechanism is not clear. They just always try different designs. I talk so much.
Yeah, sorry, I had some ad hoc connection issues. So I missed the Q&A session. I hope you already answered the two questions I'd like to ask. One is the challenges he and his team faced, and the other one is the roadmap for the next 6 months or the next year.
Okay, yeah. Thanks. I just
thank you.
While you are off, like I have introduced the background of the method. Like the first concept is from 1967, and by people doing research in 1987. There's a group in MIT, and also in the first years in 21st century university in Waseda in Japan. They have done a lot of experiments, but still it's quite new. So the first challenge is how to transport a large mass, like the top particle have pressure on the particle underneath. So if there's large mass, high load particle on the surface, it's quite hard to be transported. So in order to overcome this challenge, we have done the literature review. We have summarized all the work that people have done previously, and we want to figure out the gaps, the research gaps. So the first research gap is there's no combination between experiment and simulations. So their experiment can't be used to confirm their simulation model, and their simulation model also is not good for them to estimate or predict the performance in experiments. So the first thing we do is trying to build the connections between experiment and the simulation model. How to build the connection? We first have done the single particle experiment. If we do multiple particle experiment, it's hard to conclude the regularity or the trend concurrence from the experiment. So we first did single particle experiment. Like we have classified particles motion mode. They have different typical motion modes, so we could connect our experiment and the simulations well. Yeah, so this what we do. And also we have done, according to this basic mechanism. So within the knowledge between the experiment and simulations, we have, based on this concurrence, we have done the further test. And we have designed different parameters. So finally, we could get this kind of design, and this has high transportability. And
yeah, thank you so much for elaborating more on that. And what are you and your team planning to, like, what kind of task or challenges are you guys planning to tackle for the next year or for the next half year?
Oh yeah, so the next step. So currently the particle that we use is the normal particle, not the noodle particle. So the next step, we want to use the noodle particle, noodle simulant particle, the particle with same properties with particle on the move. So this more convincing if we could use our system to transport and separate particle similar to the particle on the move. This is more convincing, make people know that our system is available to on the move. This is the next step, and also we want to have more cooperations with other universities or other space agencies or the companies like yours, the DoraHacks, this kind of high technology companies. We could share our work with more people, and we can do more collaborations with others. Yeah. This is a quite exciting technology.
Yeah, it sounds really exciting, and I'm really looking forward to what you and your team can build for the next year. And I'm wondering, what is the best way for our audience to reach to you guys if they want to ask you questions or want to build collaborations? What is the best way for them to reach you?
Okay, I can show my. So this is our team. Can you see my screen?
It's loading now. Yeah, we can see it now.
Yeah, this is my email address. If you have any questions, you can just feel free to email me. Also, I have web pages. Like we have Imperial web pages. This is my web page, and also you can search our name, like our professor, anyone.
Great. Sounds
yeah,
awesome.
we are a research team at Imperial, so it's very easy for you to find us.
Yes, audience, if you are passionate about this ETW system for particle transportation and separation, and if you have something to share to the team, or you want to have collaboration with the team, please feel free to reach out to Yue and his team. And just once again, I really want to say a huge thank you to Yue for joining us today for this incredibly thorough and insightful demo. I really appreciated your time and effort. Just before we wrap up, I want to say once again that this Space Resources and Exploration Grant is a long-term initiative from DoraHacks that aims to foster long-term building and encourage innovation in the space sector. We are so excited to have this program, and we already witnessed some great projects and promising teams emerging. And we encourage everyone who's building projects within this space sector to join us. If you want to learn more about the Space Resources and Exploration Grant, or just DoraHacks in general, please don't hesitate to reach out to us. You can visit our website at dorahacks.io. You can also follow us on Twitter at DoraHacks, or connect with us on Telegram on DoraHacks Official. So with that being said, I just want to say one more time, a huge thank you to Yue for taking the time to be here. And thank you to all the audience who are joining us today. And that's conclude the episode 2 of our Space Resources and Exploration Grant Demo Day. Thanks, everyone. We'll see you soon. Have a good one. Bye-bye.
Thank you. Thank you very much. All right. Take care.